So today we're doing a section on factoring called solving by taking roots. So again, solving means that we will be finding specific values for the variable, not just factoring it to get the factors of the polynomial, but to actually find out what the values of those variables are. So solving by taking roots, we'll just jump right in. So example 1, we've got x squared minus 81 is equal to 0. And remember from the past couple of sections that we've done together that the number of solutions that you have to this type of a polynomial is equal to the highest power in the polynomial. So that means when we solve this polynomial, we are going to get two solutions, okay? So this is a very, very basic equation. We will add 81 to both sides, and in order to undo the squaring, we will take the square root of both sides. The square root of x squared is x. The square root of 81 is 9, but, and this is a really, really, really big but, we have to have two solutions for that polynomial. So far, we've only got one. But remember that if you square a 9 positive, you'll get 81. Also remember that if you square a negative number, you will also get back a positive. So the square root of 81 is plus or minus 9, okay? And that's what that symbol is, plus with a minus underneath, means that the x will either equal positive 9 or negative 9, and those are your two solutions, okay? So solving by taking roots is literally done by square rooting both sides. So if x squared minus 25 is equal to 0, x squared is equal to 25, and taking the square root of both sides gives us that x is equal to plus or minus 5. Very simple, okay? And of course, things will get a little bit more complicated as we go on. First and foremost, what we're going to do is, in example 2, learn how to simplify radicals. For example, we'll do a whole bunch of these. The square root of 12, the square root of 108, the square root of, 204, okay, and the square root of 10, okay? The way this is done is by using the factor tree, the prime factorization of each one of these. So we'll start off with 12. And here's the best way to do this, okay? We're looking for the square root of 12. So that's what we're going to start with in the left column. What goes in the right column is the smallest prime number that divides 12 evenly. So prime numbers are 2, 3, 5, 7, 11, etc. Okay? The smallest prime that divides 12 is 2. 12 divided by 2 is 6. The smallest prime that divides 6 evenly is 2. 6 divided by 2 is 3. The smallest prime that divides 3 evenly is 3. 3 divided by 3 is 1. And when you end up with a 1 at the bottom right or the bottom left, you're done. Okay, so now because we're doing a square root, okay, we're going to go to the right-hand column and match numbers in groups of 2 that are like. In other words, I've got 2 2s here, grouping in groups of 2, and then I've got a dangler guy, okay? So out of the grouping of 2, we're going to pull one of those that goes outside the radical, and what goes under the radical is the dangler guy. So 12 is the same thing as 2 times the square root of 3. Now we'll do the same thing with 108. Okay, so the square root of 108, so I'll put 108 on the left. The smallest prime that divides that evenly is 2. 108 divided by 2 is 54. The smallest prime that divides that is 2, which is 27. Sorry. 54 divided by 2 is 27. The smallest prime that divides 27 evenly is 3. 27 divided by 3 is 9. The smallest prime that divides 9 is 3. 9 divided by 3 is 3. The smallest prime that divides 3 is 3. And 3 divided by 3 is 1. Okay? So again, because we've got a square root here, we're looking to match the like terms or the like numbers on the right in groups of 2. So I've got 2 2s, I've got 2 3s, and that one dangler guy. Okay? So I'm going to pull one of these, I'm going to pull one of those, and the product of those will go on the outside of the radical, and the one dangler guy goes underneath. So the square root of 108 is 6 times the square root of 3. Okay, now we'll use the same idea to simplify the radical of 204. Okay, so the smallest prime that divides 204 evenly is 2, and that will give you 102. And again, the smallest prime that divides it evenly is 2, giving you 51. The smallest prime that divides 51 is 3. 51 divided by 3 is 17. And the smallest prime that divides 17 is 17. And then we get a 1. So my groups of 2, I've got 2 2s, and I've got both of these dangler guys. Okay, so what that means is I'm going to pull one of those from the group of 2s, and that number will always go outside the radical. Now I've got 2 numbers that don't have a pair. So I will multiply those under the radical to get 2 times the square root of 51. That is the simplification of the square root of 204. Okay, now lastly, we're going to simplify the square root of 10. Okay, the smallest prime that divides 10 is 2. 10 divided by 2 is 5. The smallest prime that divides 5 is 5. So if you look on the right side, we don't have anything actually that's got a pair. So that means that the square root of 10 is already its simplest form. Okay, that is the easiest way I know of to teach how to simplify radicals. Okay, the only thing you need to know are what your prime numbers are. 2, 3, everything divides by 1, so we're discounting a 1. 2, 3, 5, 7, not 9, because 9 is 3 times 3, 11, 13, 17, etc. All you need to know are your prime numbers in order to use that method of simplification. Okay, so that means that as we move forward in these examples, we're going to have more of that type of simplification that is going to be needed here. Okay, so for this one, we're going to add 100 to both sides. Okay, and then divide by 3. Okay, so here we're going to square root both sides, okay, to get x is equal to plus or minus the square root of 100 over 3. Okay, now we're going to learn a little bit of our property rules here that will make the simplification easier. And then we're going to talk about something called rationalizing, okay? So the first property is that if we've got the radical of a fraction, that we can split up the top and the bottom, and each one of them get their own radical, okay? So the square root of 100 over 3 is the same thing as the square root of 100 over the square root of 3. Okay, and the reason that's important is because 100 is a perfect square. The square root of 100 is 10, and 3, that doesn't simplify because 3 is prime. So now we're going to rationalize the denominator. What that means is that some person decided at some point, some mathematician decided at some point that you're not allowed to leave a radical in a denominator. So we rationalize it away by multiplying whatever that radical is over itself into our original fraction. So in the bottom, we've got the square root of 3. So we will multiply that by the original fraction by root 3 over root 3, because this fraction here is equal to 1. Okay, anything over itself is equal to 1. Now we multiply straight across the top and get 10 times the square root of 3. Then we multiply straight across the bottom. The square root of 3 times the square root of 3 is the square root of 9. But remember that the square root of 9 is, in fact, 9 is a perfect square, which is 3. So the trick here is whatever you've got under your fraction there in your denominator, when you multiply the square root of a number times the square root of that same number, you will get that number as an answer. In other words, the square root of 5 times the square root of 5 is 5. The square root of 7 times the square root of 7 is 7. The square root of 6 times the square root of 6 is 6, etc. Okay? So that simplification then, by rationalizing, allows us to remove the radical from the denominator. Okay? And that is a very important thing. Okay? So now we're going to go to something like example 4. 4 times, and here is our squared thing right there. Okay. Okay. Then it says state the solutions as both simplified radical expressions and as a solution set containing the decimal. Okay. So we need the radical answer simplified and the decimal equivalents, which will be found on our calculator. Okay, so we're going to solve this as we would a regular equation by subtracting 6 from both sides. Okay, so we will subtract 6 from both sides and get 108. Okay, then the next step is to divide away the 4 that's out front, because we need to isolate that squared term there so we can eventually solve for y. Okay, now we're at the point where we're going to solve by taking roots. Square root both sides, and on the left, the square root of y minus 2 squared is y minus 2. The square root of 27 is plus or minus the square root of 27, which we will use our simplifying table to simplify. The square root, okay? So the lowest prime that divides 27 is 3. We get 9 divided by 3 is 3. Divided by 3 is 1. So we're going to group those in groups of 2. So I've got 2 3s and 1 loner guy. I'm going to pull one of those out of the pair, set that outside the radical, and the straggler guy goes underneath the radical. So the square root of 27 is 3 root 3. Okay? Now, in order to get y alone, we're going to add 2 to both sides. So y is going to equal 2 plus or minus 3 times the square root of 3. So we'll separate these in order to get the decimal equivalents. The first thing is going to be paying attention to the plus sign, and then we will be paying attention to the minus sign. Okay? So as far as the plus sign goes, y is equal to 2 plus 3 times the square root of 3. Okay? So you can enter that into your calculator, literally exactly the way you see it. 3 times the square root of 3 is equal to, decimal rounded to the 2 places, let's just round it to 3 places, 7.196. That's the decimal equivalence of 2 plus 3 times the square root of 3. Then we've also got 2 minus 3 times the square root of 3. So 2 minus 3 root 3 is negative 3.196. So those are the two values in radical form, and then the decimal equivalent rounded to 3 decimal places. Okay? Now what we're going to do is work on example 6, okay, imaginary. So we've got x squared plus 25 is equal to 0. So when we go to solve this for x squared, we get a negative 25, and taking the square root of both sides, we get a negative under our radical. So remember, when you've got a negative under an even index radical, like a square root, a fourth root, a sixth root, etc., having a negative under there is not going to work. So these are the things that we need to remember. I squared is equal to negative 1, and the square root of I squared is equal to I. All right, so we're going to work on simplifying the square root of negative 25 by rewriting it as negative 1 times positive 25. Now, if you look up at the key, we see that negative 1 can be replaced with I squared. Okay, now we'll continue. The square root of I squared is I, and the square root of 25 is 5. So writing that in standard form, x is equal to plus or minus 5i. So let's do another one of those. Okay, we'll say x squared plus 9 is equal to 0. So we'll subtract 9 from both sides and then take the square root of both sides. Okay, this can be rewritten as negative 1 times 9, which can then be rewritten as I squared times 9. The square root of I squared is I. The square root of 9 is 3. So x is equal to plus or minus 3i. Now, of course, they're not always going to be that simple. We might have x squared plus 12 is equal to 0. Okay, so we will perform the same operations as we go through this. But if you recall, the square root of 12 does not have a perfect square. It's got a number as a perfect square and then a dangler guy that's going to stay behind. Okay, so x will equal plus or minus the square root of negative 1 times 12, which can also then be rewritten as the square root of I squared times 12. Well, the square root of I squared is I, but we need to remember that the square root of 12 has to be simplified. So 12 divides by 2, 6 divides by 2, 3 divides by 3 to get a 1. So the simplification of the square root of 12 is 2 times the square root of 3. Okay, so in standard form, x would be equal to plus or minus 2I times the square root of 3. Okay, so there are, when you've got a negative under your radical, the simplification methods that we used are still applicable. We just need to remember that if it's not a perfect square, we're going to still have to use our table over here to simplify the radical, and then remember to add the I. So the last example is this one here, okay? The first thing that we'll do is subtract 10 from both sides to get a negative 8, okay? Then divide both sides by 2 in order to isolate the squared term, and then we're at the point where we can solve by taking roots. Square root both sides. And do not forget the plus or minus. I guarantee you at least a quarter to a third of you will forget the plus or minus, and you'll get one answer at the end of all of this, and it will be wrong. Okay? So the square root of negative 4 can be rewritten as plus or minus negative 1 times positive 4, which can be rewritten as I squared times 4, which is the square root of I squared is I, the square root of 4 is 2. So in standard form, what we've got so far is x plus 3 is equal to plus or minus 2I. Then we will subtract 3 from both sides and get our two solutions this way. One of them is negative 3 plus 2I, and the other one is negative 3 minus 2I. And those are called conjugates. And that is a very, very, very important term that we're going to use as we go forward into factoring. Okay? So, don't forget that when you've got a negative under your radical, that you need to remember that that is an imaginary solution with the number I. Okay? Good. Very simple. Awesome.